Hi everyone, welcome back to Transport 2 with Anthony. So this time around we actually have a pretty cool problem here. We have a open container, and inside the container is a mixture of acetone and methanol. Now over top of this container we have air blowing, and there's actually a screen on top of this container, and this prevents any turbulence from the air inside the container. So we don't need to worry about any of that. What we do want to know is we want to know what the molar flux of acetone and methanol are as they evaporate from this mixture down here and move upward. And then after we do that, what we want is we want to have a composition profile of the three gases as we move along from z equals 0 to z equals delta. So in order to actually calculate the molar fluxes of acetone and methanol, what we're going to use is the Stefan-Maxwell equation. And what the Stefan-Maxwell equation does is it describes the interactions between two components. But in the case of this problem, we actually have three components. So because of that, we're actually going to have two different Stefan-Maxwell equations. So I'm going to go ahead and write those two equations down. And we're going to start with component 1. So the change in the mole fraction of component 1 over the change in distance z is equal to the mole fraction of component 1 times the molar flux of component 2. We're going to do the interaction between component 1 and 2 first, or component 1 and the other two components, minus the mole fraction of component 2 times the molar flux of component 1 divided by concentration times the Stefan-Maxwell diffusion coefficients between component 1 and 2. Then to that we're going to add we're going to do the exact same expression, but instead of between 1 and 2, we're going to do it between 1 and 3. So we're going to write the exact same thing. We're just going to replace the 2's with 3's. And this equation right here is really describing the interactions between component 1 and component 3, or between component 1 and 2 and 1 and 3. So now we're going to do the same thing for component 2. So the change in mole fraction of component 2 over the change in z distance is equal to the mole fraction of component 2 times the molar flux of component 1 minus the mole fraction of component 1 times the molar flux of component 2 divided by concentration times the Stefan-Maxwell coefficient of diffusion between 1 and 2 again. And then we're going to add, again, the same thing. We're just going to replace 1 with 3. So now that we have these two written down, we'll do 2, 3. A way we can kind of simplify this is first recognizing this Y3, this molar fraction of air. We know that mole fractions should all add up to 1, so we can rewrite the mole fraction of component 3 as 1 minus y2 minus y1. And this is just based on the definition of mole fractions. And what this does is it just effectively gets rid of a variable. It makes our overall equation just a little bit easier to deal with. And then another thing that we should recognize is that since if we're considering the liquid-vapor interface right here, there is no air that's going into the mixture. There is no diffusion happening there. And if there's no diffusion happening there, since we're working with a rectangular system here, according to the equation of continuity, all throughout this entire system, the diffusion, the molar flux of air is equal to 0. And that's from the equation of continuity. Again, if it's 0 at the interface, it must be 0 all throughout. So that lets us remove this term and this term, since n3 is 0. Okay, so what we're left with here is two differential equations. And these are simultaneous differential equations. Since we have two equations here, we're solving for n1 and n2. We're going to have to solve these. And while we could do it by hand, we're actually going to use Python for this. But the way that we're going to find the solution is that we're given initial values, and these are up here, where we see y1 initial equals 0.3, y2 initial equals 0.5. These are our initial values for the mole fraction of acetone and methanol, and we're going to approach it as an initial value problem. So what we're going to do is we're going to solve the differential equation. Well, we're going to make a guess for what the molar flux of acetone and methanol are going to be. Once we make that guess, we're going to solve the differential equation, and we're going to see what we get as values at delta, because we know that at delta, when z equals delta, the mole fraction of air is 1. It's only air, which means that the mole fraction of component 1 and 2 must be 0. So what we want is to make a guess for n1 and n2 such that when we solve the differential equation from 0 to delta, at delta, the values of y1 and y2 are 0. And in order to do that, it would be quite difficult to do that by hand, so we're actually going to use Python for that again, and we're going to set it up as a root solver. So before we actually go on to solving this using Python, we want to get a good order of magnitude estimate for a couple reasons. First, for actually using our root solver, we need a good order of magnitude estimate for the molar fluxes. And also, when we're going to do something called scaling, where we scale our dependent and independent variables to hold values between 0 and 1, and that actually it makes it easier, and it's just better for the computer to solve it using values between 0 and 1. Less of a chance of an error. So we're going to go down here and we're going to do scaling. And again, what scaling is we are trying to get values. We are going to scale our dependent and independent variables to be between 0 and 1. So to start off with our dependent variable, y1, this is a mole fraction, and mole fractions, they are already between 0 and 1, so we don't actually have to scale this at all. We can leave this how it is. Now, z, our variable z, goes from 0 to delta, which delta is 0.24. So this is not between 0 and 1, this is between 0 and 0.24. So we're going to define a new variable called eta, which this is going to be our independent variable divided by our max distance delta. And this is really the key to scaling. Because once we do this, our eta is going to go from 0 to 1. Because when when we divide the our independent variable by delta, it will result in values between 0 and 1 rather than between 0 and 0.24. So we're going to rewrite this left-hand side of the Stefan-Maxwell equation with eta instead of z. So I'm going to use the top one up here. And we have dy1 over d eta times, and this is from the chain rule, times d eta over dz. Again, this is equal to this up here. Now the next thing I'm going to do is actually solve d eta over dz. And d eta over dz is just 1 over delta. So what we're left with is this on the left-hand side, and I'm just going to copy down our right-hand side. Okay, and I'm going to, right now we're trying to get an order of magnitude estimate. So I'm only going to work with this first term in the Stefan-Maxwell equation because we're going to get the same order of magnitude for the second term. So really for our estimation purposes, we can just leave it out. We'll still get the same order of magnitude. So I'm going to go ahead and multiply delta over and I'm going to rewrite this. So the change in the mole fraction over the change in eta equals this top part of the Stefan-Maxwell equation divided by concentration times the Stefan-Maxwell coefficient of diffusion between 1 and 2 divided by delta. Okay, so now what we want to do is we want to plug in our order of magnitudes for each variable. And we're going to start with this by making an estimate on what this right here is. So I'm going to draw this out like a graph, well, as a graph. And let me make sure that's right. Yeah, so our mole fraction of acetone starts at 0.3, and eta goes from 0 to 1. And we know there's a point there because it starts at 0.3. And we know that when, that's not 0, this is 1. We know that when eta is 1, the mole fraction is 0 because it's completely air. It's all air. So we're going to estimate what this line looks like. And that should be a straight line. Since we're estimating, we can say it's a straight line. In reality, it might not look like a straight line. It might be curved like that, like that. It even might look like this, which would kind of, it wouldn't make our estimation too accurate if the line was over here. But we're just going to estimate that it's straight for our purposes. So that gives us the value of 1 as the derivative. Copy this down. Now for our concentration, we know that equals P over RT. Delta. So our pressure is about 100 kPa, so that's going to give us an order of magnitude of about 10 to the 5th. Divided by R times T. R is going to be about 10. Again, this is an estimation. So we'll call that 10 times temperature, which is about 300. If we do about 10 times 300, that's about 3,000. And that's going to be about the order of 1,000. again, this is all estimation. So we'll call that 10 to the third times our coefficient, our Stefan-Maxwell coefficient of diffusion. This is 8.48 millimeters squared per second. So this is going to be about 10 to the negative 5. And then our delta is 1 from scaling. So these cancel, and we're left with 10 to the negative 3. So I will put 10 to the negative 3 down here. 10 to the negative 3. Now, y1, y2, these are mole fractions of acetone and methanol. These are going to be between 0 and 1. So order of magnitude is about 1. So these don't really play a part, which leaves us with our molar fluxes need to be 10 to the negative third in order to make this expression equal to 1. These must be 10 to the negative third order of magnitude. So from scaling, we scaled our independent and dependent variable to be between 0 and 1. In this case, we only had to scale the independent variable. And from that, we were able to estimate the order of magnitude of the molar fluxes of component 1 and component 2. And we found that they should be about 10 to the negative third. So that's our scaling. And from here, what we're going to do is we're going to go over to Python, where we're going to solve the initial value problems. We're going to solve these Stefan-Maxwell equations from 0 to delta. And we're going to use a root solver to find values for n1 and n2 such that the initial value problem gives us values of y1 and y2 equal to 0 when we're at delta. So I will see you over in Python. Thank you.